Day 39, Honors Physics, Newton's Three Laws, Example 41. So part A here, you've pushed a sled onto a frozen lake which has low friction but some friction. It's not that there's no friction, there's some. A small force of friction which is going to stop this sled. But it's going to go quite a ways, hopefully, because that's kind of the fun of this, the experience here if you're actually on this sled. The sticking point on this problem, I've known from past years, is that it's tempting right now to put a forward force or a pushing force on the sled. No, the sled was pushed and it's no longer being pushed. Somebody was pushing for a while, they let go, now the sled is just sliding and coming to a stop because of the force of friction. Nobody is continuing to push this sled. So you have to resist the temptation to put a forward force on the sled. That would have been true while it was being accelerated, but now it's decelerating because of friction. Well, so this is just F net equals ma. And F net, there's one force, that's the net force, that's the force of friction, equals the mass of the sled, 70 times A. Well, it seems like we have two unknowns. However, we can do a side calculation or we can do a substitution in here for force of friction. They give us the coefficient of friction, so I could do the calculation for the force of friction, kinetic friction. The force of friction is mu times the normal force, and the normal force is 700 and the friction coefficient is given, so the force of friction is 0.05 times 700. That will give us the force of friction. Once we have that, you can plug in here to get the acceleration. So the acceleration will be known. All right? Now I'm out of space down here. I'm going to go up to the top. Once you have the acceleration, part A is asking for how far the sled goes. So you're going to have a v sub I of 12 meters per second. And have a v sub f of 0. You're going to have an acceleration that you know that is actually a negative. It's going to be important to put a negative in there. It's going to be the answer to part A, but you have to put a negative in there. It's slowing down. So you'll know that, and then S and T. So I believe if you take the fourth equation, that is v sub f squared equals v sub I squared plus 2as, you'll know everything but S. So plug those all in, making sure A is negative, and that will give you the total displacement that the sled slides on the ice. All right, then in part B, let me use blue. In part B, the sled now comes to a stop and you got to get it going again. So static friction is generally higher, or can be higher, than kinetic friction, and it matches you up to a point. If the coefficient of static friction is 0.10, its maximum value, F friction max for static, the first case was kinetic, is equal to mu times the normal force. So it can be less than that. I'm not considering that right now. But the maximum frictional value, static, it says maximum, is mu, which is 0.10, times the normal force, which is 700 still. So the maximum value is basically 70 newtons. So if the coefficient is 0.10, what force is necessary to start the sled moving again? 70 newtons. You're going to need 70 newtons to get the sled sliding again. So that is the answer to part B. Or something slightly bigger than that, 70.01. Anything less than that, friction will match. If you push with 50 newtons, friction will match it. Static friction will match it at 50 newtons. Until you get to 70 or anything over 70, that's the minimum you'll need to get the sled going. Something 70 or greater.